Professor Bialis here. In this video, we're going to be talking about section 4.1, where we introduce the idea of a system of equations. Now, throughout this chapter, we're going to be talking about different ways that we can solve these systems. We're going to start with the most fundamental way, which is graphing. Okay, but before we get into graphing these and solving them that way, I want to talk about what these are, how they look, and what the answers are going to look like. So again, this is section 4.1. We're solving systems with graphing. Okay. Now, all a system of equations is a collection of two or more equations that we're kind of thinking about and using at the exact same time. Okay, so when we're looking for a solution, remember, if we're dealing with a line, there's going to be an infinite number of solutions. But for a system, we want to find the one solution that will work for every equation in the system. So that's a little bit of a different scenario. Let's see what this looks like. Let's say we have a system like this. Those are two regular equations, regular linear equations, but we're working with them at the exact same time. Now, that's what a system would look like, but then the question is going to be at first, is a certain solution correct or not? Now, a solution is not going to be 5 or 13. It's going to be an ordered pair because we need to have numbers for the x and the y that work together. So the question is going to be, is 3, -2 a solution, okay, to this system? Now, as always, when we're checking if an answer works, you plug it in, you see if it works. Here's the little extra piece here. It can't just work for one. It has to work for all members of the system for it to be a true solution. So when I plug this in, first one, I've got 2x minus y equals 8. 3 in for x, -2 in for y. That's a 6 plus 2, that's an 8. That works. Okay, so it's an answer, right? Not yet. We know that it works for the first one. This is a point on this line. Remember, all a line is when we graph it is a picture of all the answers to that equation. Okay, so we know that this point falls on this line. Does it also fall on this line? So if I plug that in, x plus 3y equals 4. 3, -2, so 3 minus 6, that's a -3. That does not work. So this does not work for both, therefore it is not a solution to the system. It's a solution to this guy, but not this one. Okay, so in this case, is a solution? No. Okay, let's look at another one. Now we have a new system. We're asking if this is a solution. And again, this will all be given to you in the first few problems of this chapter. Okay, now let's check it. I have 5x minus 2y equals -3. Plug in the x, plug in the y. 15 minus 18, -3. That works. Okay. Now, again, we have to verify that it works for both. So let's continue. I've got y equals 3x. Now careful, the y goes first, then the x. And we have 9 equals 9. So in this case, yes, it worked for both. Therefore, this is a solution. Okay, what that tells me is this ordered pair is a point on this line and on that line at the same time. Okay, so now let's practice finding those solutions ourselves. Okay, and one more thing before I move on, just so we're aware, like in this case, 3 comma 9 is a solution. It is a single solution, a single ordered pair solution. A lot of people think of that as 2 different answers, but there's only one answer there. So now I want to solve by graphing. Let's say we have that. Okay, now we have a system of 2 equations. Okay, what I would suggest you do, we can graph these using a table of values, using intercepts, or using slope-intercept form. I would use slope-intercept form, simply because we can get a lot of points, therefore we get a more accurate line. These 2 equations need to be graphed very accurately because what we're going to be looking for is the point where they cross. And if I graph a line and I'm slightly off, that can throw off the entire answer. So I need to make these as accurate as I possibly can. So what I'm going to do is start by getting these both in a graphable form. What I mean by that is slope-intercept form, solve for y. So I'm going to add a 3x. And then here, I'm going to subtract the x. And then I could divide by a -1 or really just change the signs. So I've got y equals x minus 6. And we have that. Okay? So let's see how these 2 play out graphically. Okay, first one. I'm going to start by going down 10. 2, 4, 6, 8, 10. And then I have a slope of 3, or 3 over 1. So I'm going to go up 3, right 1. 2 points determine a line. However, keep going. Again, the more points you have, the more accurate your line is. Up 3 over 1. Especially on this first one. And I'll explain why I mentioned the first one in a second. Okay? I could also go down 3, left 1. So let me get that straight edge. Let's connect these dots. There. Okay. Now, remember, a line is simply a picture of all the ordered pair solutions to an equation. Okay, so I found this, and then I went up and over. Those are 2 solutions to that first equation. Here's another one, here's another one, here's another one. All these points in between are also solutions to that equation. Okay? Now, if I were to graph the other one, I start by going down 6. 2, 4, 6. And then I have a slope of 1. Up 1, right 1. Up 1, right 1. Now watch what happens. I just hit that point that was already there. At this point, I am on both the red line and the blue line. So that right there shows a solution that works for both. So I draw this line, and this point right here is my solution to the system of equations. So that is 2, -4. Okay? So what we're doing is graphing 2 lines, seeing where they cross, because where they cross is a point that falls on both lines, therefore is a solution to both equations. Nothing more to it than that. If you want to check your answer, as always, you can plug them into both, make sure it works for both, and then you'll be fine. Okay, let's look at a few more examples. let's say we have x plus 3y equals negative 1. And y equals 1. So here's another system. Again, what we're trying to do is first get them both in a graphable format, slope-intercept form. So this one's already good because we know y equals 1, that's a horizontal line. Now that tells me a couple things. First of all, we know that we're going to have a very easily graphed horizontal line. Like so. However, it also means y has to be 1. The solution to this system has to be an ordered pair with a y value of 1. Okay? And we're going to talk a little bit more about the algebraic ramifications of all this in the later sections. Okay, but we can start thinking about it here. Y equals 1, the y better be 1. For this to work, the y has to be 1. Now, let's go to the first equation. Let's solve that for y. Subtract x. And then divide everything by 3. And we got that. Okay? Now, be very careful with this because I keep saying we need accurate lines, and now we're forced to approximate a little bit. So just take your time, be careful. So I'm going to have a line that starts by going down 1/3, which is about right here. And then I go down 1, so 1 lane, and right 3. Okay, notice I'm still in the same kind of position at each of those lanes. Now as you can see, I'm going to drop down. I'm not going to cross down here. I'm going to cross over here. Let's maybe go this way a little bit more. So instead of down and right, I can go up and left. Up and left. Now, it wasn't so nice as the last one where we just hit a point that was already there. So what I would suggest you do to make sure this line is as accurate as you can make it, I would continue on. I know I'm going to cross somewhere here, but I want to make sure I'm not, tweaking my line at the end. So I'm going to go with this and this, and then here I can go down and over like so. Okay? Now again, make sure that that line is as accurate as possible. Okay? Now, where did we cross? I had to approximate, so my line might be a little off. Please keep that in mind. But it would be really nice if it was this point right here, which would be -4, 1. Whoops. -4, 1. Now, what I would suggest, since there was so much approximating going on, double check that. Okay? So, I have -4, 1. Definitely the y is 1 is good here. If I plug in -4 plus 3 times 1, -4 plus 3, -1, we're good. Is it possible for you to cross somewhere like this, where you have some fractional answer? Absolutely, that's possible. However, I'm not going to give you something like that. There are other methods to use when you get answers like this, and I'm going to show you that in the later sections. So when you're graphing, the examples I'm going to show you are typically going to work out nicely, simply because what's the point of approximating when we're doing this? Sometimes that happens, but I'm not going to be quizzing you, testing you on something like that. So again, keep that in mind when you're doing these graphs. Okay, let's look at a couple more. How about this? Okay, now, first thing, get them in a graphable form. I would do both of them at the same time, and I'll explain why in just a second here. So I've got 3x minus y equals 6, 6x equals 2y. Okay, solving for y, I'm going to subtract 3x. Negative y is negative 3x plus 6. And then I'm going to divide by a negative 1. So y equals 3x minus 6. Okay, I see some people, they want to stop and graph that first. I don't like that because you're kind of bouncing. You're solving, then graphing, then solving, then graphing. It's very easy to lose focus. Also, watch what's going to happen. If I divide by 2, I get y equals 3x. Do you notice anything about those lines? These two lines have the same exact slope. What does that mean? That means that they're parallel. Parallel lines never what? They never intersect. What have we been looking for this entire time? Where do they cross? They're not going to cross. So if that's the case, honestly, don't even bother graphing. If you can look at this and tell me they're not going to cross because I know they're parallel, that shows me you know what you're talking about. Okay, so in this case, I have these two. I know that they're never going to cross, therefore, no solution. Okay, one thing I do ask my students when I have a face-to-face class, when we're doing things on paper, is if I say solve this by graphing and you see that it's no solution, I'm not going to make you graph, but somewhere on the graph write parallel lines. Okay, that tells me why you didn't graph. Okay, if you have a different instructor, then ask them how they would want. Some of them will ask you to still graph. But if it's me, I still want to see no solution. That's your answer. This just explains why you didn't bother graphing. Okay, and I'm okay with that because that shows that you knew what was happening ahead of the game. Okay, but please specify that's the reason why. Okay, let's look at another one. Okay, first thing, get them in a graphable form. Okay, solving for y, subtract 3x. Divide by 4. That's now ready to be graphed. Again, if you want to graph it right now, you can, but I would suggest just keep the same mindset, solve that one for y. Okay? So I'm going to subtract 9x. And then divide by 12. And there we go. Now, what do you notice? Are these parallel? They're not. They have the same slope, but they also have the same y-intercept. That means they're the exact same line. Now, what does that mean to us? Okay, if these are the exact same line, that means if I graph one and I graph the other one right on top of it, that means they're crossing, but everywhere. So when they were parallel, there was no solution. But when they're the exact same line, that's when we have infinitely many solutions. However, I don't want you to just write there's infinitely many. That tells me how many there are, but it doesn't tell me what they are. So this is how I write my answer. When they're the same line, I can skip the graph and just say, I'm not graphing because they're the same line. Okay, write that down just so I can see why you didn't bother graphing. Okay, but now what's the actual answer? The answer is this. I'm going to have an infinite number of ordered pair solutions. So I'm going to say it's the set of all xy ordered pairs such that, and then I'm going to write down any of the equations I have in front of me. Okay, I can write down this one, I can write this, I can write this. Typically the one that's written is the standard form that has the smaller values to it. But any one of the three would work. So I'm going to write 3x plus 4y equals 12. Okay, that is your answer. You're saying that I will take any xy ordered pair, but it has to work in this equation. So I'm not just taking any point on that grid. It has to be on this line. Okay, because if it's on this line, then it's the same as this, it's the same as this. So that's how I write my answer. X comma y such that, and then I write one of the equations. Okay? So with systems, we are solving with graphing by graphing them and seeing where they cross. That would be a solution that they have in common. Now, like I said before, if they cross somewhere like this, where it's kind of in the middle of nowhere, we would have to approximate that if we're using graphing. However, there's algebraic methods that we're going to talk about in the next two sections where we can get something exact. So even if it's 11/13 comma 17/27, we can get that exactly. We wouldn't be able to get that off of a graph, okay? But we can get it algebraically, and we'll talk about that in future videos, okay? So, as always, if you have any questions, let me know. Continue to work hard, and I'll see you next time.